Now this here is one of my favorite units of all time. It's the zeros of polynomial functions. So we talked in the previous section about how if f of k equals 0, we know that x minus k must be a factor, and we saw a couple of those. And again, if x minus k is a factor, we also know that f of k equals 0, and that is a 0. So the factor theorem states that a polynomial x minus k is a factor of the polynomial only if f of k equals 0, and we use synthetic division to check that. The number of zeros theorem says that a function defined by a polynomial degree n has at most n distinct zeros. So a fourth degree polynomial will have 4 zeros. A fifth degree polynomial will have 5 zeros. Now the number of distinct zeros means the number of unique or non-repeating zeros. Sometimes a zero will repeat, and we call that a multiplicity. So for example, x squared has a 0 of x, and that's the only zero, that's the only place a 0 of 0, x equals 0, because that's the only place that it intercepts the x-axis. But it has that 0 twice. So we will always have a number of zeros equal to the degree of the polynomial. We just may have some that repeat, and we call that a multiplicity. So we want to decide if the given binomial is a factor of f of x. So we're going to use synthetic division and the factor theorem to determine this. So if we have x minus 1, again, this is in the form x minus k. So k is 1. We're going to put 1 inside the box. We're going to set out our coefficients. So we've got 2. We need a placeholder 0 for the 3. And we have 3, -5, and 7. So we're going to go through this process. We're going to add, we'll multiply, we'll add, we'll multiply, we'll add, we'll multiply, we'll add, we'll multiply, and we'll add. So we get a remainder of 7. So that means that because f of 1 does not equal 0, then no, x minus 1 is not a factor. Here we've got the same factor, so we're going to use the same value of k. We're going to use 1, 2. We're missing the linear term, so we need the placeholder 0, and then the -3. So we'll add, we'll multiply, we'll add, multiply, add, multiply, and we get 0. So because f of 1 equals 0, then yes, x minus 1 is a factor. And again, like I mentioned in a previous unit, our quotient here is the other factor. So we've factorized this problem into x minus 1 and then x squared minus 3x plus 3. And then if we could factor the x squared minus 3x plus 3, we would. This polynomial is prime, so we can't, but we have been able to factorize this polynomial a little bit. So to start, we're going to be given a 0 for a polynomial to get us started and use that to factor it, and then we're going to use our other factoring techniques of quadratics in order to finish. So what's important with these high degree polynomials is that we need to get down to a quadratic, and then we can use quadratic methods for everything else. So we'll be using synthetic division to reduce the degree as many times as we need until the quotient is a second degree polynomial. So we're given this polynomial and we want to factor it into linear factors given that -3 is a 0. They've told us it's a 0, so we know we're going to get the remainder of 0. Then once we have all the factors, we're going to state all the zeros. So we'll start with the factors. We know that -3 is a 0, so we're going to set up our synthetic division. And we'll go through the process, add, multiply, add, multiply, add, multiply, and we get the remainder of 0. We expected this. We knew that should happen. So now we're left with 6x squared plus x minus 1. So we have a quadratic. That means we can now factor this using any of our quadratic methods for factoring. So we're looking for a product of -6 and a sum of 1. That means we're going to use the numbers +3 and -2. So 6x squared, so let me write this over here, 6x squared plus 3x minus 2x minus 1. We'll factor by grouping. And now we have these linear factors. Now we want all the linear factors, and this is a third degree polynomial. That means we need 3 linear factors. Right now I have 2 listed. Well, here is where our third one lies. Remember, if f of k equals 0, then that means that x minus k is a factor. So since f of negative 3 equals 0, that means that x minus negative 3 is a factor, giving us a factor of x plus 3. There's our linear factors. Now we need the zeros. So we have our factors x minus 3, 3x minus 1, 2x plus 1, and x plus 3. Those are all of our factors. Well, we know this one gives us the 0 of x equals negative 3. We just need to solve the rest of these. So we can use our 0 factor property and solve x equals 1/3 and x equals negative 1/2. So all of our zeros are 1/3, negative 1/2, and negative 3. So we're given that 2 is a 0, so let's start it all over. 1, 6, negative 1, negative 30. We don't need any placeholder zeros. We should get a remainder of 0. If we don't, then that means we messed something up and we need to go back and double check it. So we got 1, so add, multiply, add, multiply, add, multiply, and we've got the remainder of 0. That's doing great. So we have x squared plus 8x plus 15. So now we just need to finish by factoring this. Product of 15, sum of 8, that's going to be 5 and 3. So we get x plus 5 and x plus 3. And then again, it's a third degree polynomial, so we need 3 factors. We're going back here. Since f of k equals 0, then that means that x minus k is a factor. So since f of 2 equals 0, x minus 2 is a factor. X minus 2. There's our linear factorization. And then we just need to solve these to get our zeros. So we have x plus 5, we have x plus 3, and we have x minus 2. We know that x minus 2 gives us 2 as a 0. If we use our 0 factor property, we can identify negative 5 and negative 3 as our zeros. So x equals negative 5, negative 3, and positive 2 as all of our zeros. Now here, we're given a fourth degree polynomial, which means that we have to have 4 linear factors and 4 zeros. So they're telling us that 4 is a 0 with a multiplicity of 2. So there's 2 of my zeros right there. So we're going to do synthetic division with 4 2 times to factor all the way down to a quadratic. So we'll start in here. 1, 10, 33, 40, and 16. Making sure that we've got 4, 3, 2, 1, 0. We've got all of our coefficients accounted for. And now we'll go through the process of multiplying and adding. So 1, we multiply, we add. Actually, pause there. Looking ahead, I realize this isn't going to work. I did a little bit of typo. This is supposed to be at negative 4. So we're going to use negative 4 as our 0. So correction, negative 4 is a 0. Had a little typo there. Apologize for that. So let's go ahead and fix this real quick. Negative 4, that's going to give us a 6. So picking up where we left off, negative 4 times 6 is negative 24. That'll give us a positive 9. Negative 36, that gives us a positive 4. Negative 16, that gives us a remainder of 0. So we've already factored it once, but we're still not at a quadratic. This right here, just as a side note, you don't need to write this. This is x to the third plus 6x squared plus 9x plus 4. So now we're going to use negative 4 as a 0 again on this new factored version to factor out another x plus 4. So we're going to use these same numbers. We're actually going to ignore this line here, and then we're just going to continue again with negative 4. This is a little space-saving technique. So we bring down the 1. We get negative 4, positive 2, negative 8, positive 1, negative 4, 0. Now we're left with x squared plus 2x plus 1. So now we just need to factor this. So we have a product of 1 and a sum of 2. That's going to be x plus 1 and x plus 1. And then our other factors, of course, since we have, I'm going to write this, f of negative 4 equals 0. That means that x minus negative 4 is a factor. So we have a factor of x plus 4. So our linear factorization is x plus 1, x plus 1, x plus 4, x plus 4. And we're going to write this in a shorthand of x plus 1 squared and x plus 4 squared. And that squared is what is also giving us a hint that we have this multiplicity of 2. So we can see that multiplicity is carried through by that exponent of how many times that factor appears. Now, how do we write the zeros? So we know that x equals negative 4 is a 0. So we highlight this. This is our linear factored form. And we know that x minus 1, or x equals negative 1, is also a 0. So we've got these zeros, but they're both zeros twice. So we indicate that with their multiplicities. State all zeros and their multiplicities. So x equals negative 1 with a multiplicity of 2, and x equals negative 4 with a multiplicity of 2. And there's our zeros and their multiplicities. Again, this is one of my favorite units just because it's a lot of synthetic division, which is pretty simple, clean, and straightforward, but it allows us to do a lot of work with the polynomials in a way that we've never been able to do before.